Hi and welcome to another episode of TRX Bench. Well, some of you recently asked me if I could show a little bit of FM modulation on the spectrum analyzer. And exactly that is what we want to do today. I just want to show you some FM modulation or modulated signals on the spectrum analyzer, and I want to show you a method how to be able to get out of the spectrum analyzer signal the deviation. Okay, first step, let's simply look into it, how it looks like on the spectrum analyzer, and then let's go a little bit into it that we will be able finally to get the deviation, because that is definitely an information which is not easy to get out of the signal if you do not have a dedicated modulation meter, right? So therefore, let's see how we can proceed. So first of all, we have here a carrier, right? So what we see here is a carrier without any audio information on it, right? So now a carrier for its own is senseless, because we cannot carry any information. So we put an audio signal onto our carrier, and we can do it in different ways. So there is not only one modulation, it is not only FM, it is not only AM, so there are of course some more modulations, but we want to focus today simply on frequency modulation on FM. And therefore this carrier, we will put an audio signal of 1 kilohertz to this carrier, and we do it with frequency modulation. So let me switch on the modulation, and here it is. So that is how it basically looks like. And if you have seen an AM signal, so that is definitely completely different. So we easily can do that. I switch off our FM modulation, and what I want to do is I put now an AM modulation so that you can see both modulations. And I put now an AM modulation with a modulation depth of 50% to this carrier. And now I switch it on, and here it is. So you can easily see the difference now, what a FM signal looks like and what an AM signal looks like. And if we change here our span from 40 kilohertz to 10 kilohertz, right? So you can easily see now our span is 10 kilohertz. So we can really say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means from here to there we are covering 10 kilohertz, and thus you are easily able to see that our audio signal is 1 kilohertz away from our carrier. So that is then our 1 kilohertz audio information which is put on here our signal. And now back to FM. Now I put my 1 kilohertz again to the signal, but this time on FM. And what you can see already, that the bandwidth is much wider. So you need much more channel space, right? So therefore you really have to think about what the bandwidth will be if you modulate a signal in FM. Again, let's go back to AM, okay? And let's put it on. Ah, sorry, it was already on, sorry. And you see this here, if you like, is a bandwidth. And that means in our case, if we only would transmit here our 1 kilohertz tone, so we have the upper sideband and we have the lower sideband. And that means that the entire bandwidth is 1 kilohertz plus, 1 kilohertz minus, so that is 2 kilohertz. I mean, of course, a normal conversation is not only 1 kilohertz, so if we would now change to 2 kilohertz, because our audio bandwidth, our speech bandwidth is of course more than 1 kilohertz, so it is 3 kilohertz or whatever. So therefore it is more than, of course, this 2 kilohertz. But you clearly see that the bandwidth of an AM modulated signal, it's more narrow than an FM signal. Back to FM, and you see we cannot really see it here on our entire screen. So we have to change our span, and that is what I want to do right now. And you see here, you can see the span information, and with 20 kilohertz span, so from here to there, now it is 20 kilohertz, and you already see again it is much wider. Okay, now in this information here you really cannot see the deviation, right? And that is an important information. We need to know the deviation, because as wider our deviation is, as more band space or bandwidth we need. And that means that an FM signal easily can go into your neighborhood channels and will distort your neighborhood channels. Therefore, you really need to have an eye on the bandwidth, and therefore you need to adjust the right deviation to the right channel space. And that is the reason, for instance, for all our CB radio friends, a CB radio channel is only 10 kilohertz, and therefore you cannot adjust your deviation to infinity, right? Because otherwise you really would splatter over all channels. Okay, but now let's go a little bit more into the theory behind FM. And this graph may show it very clearly. So that is from Wikipedia. You can find it if you are typing in FM radio wave, and then you see this diagram here. And it is basically that we have here our audio information, and then we have our both different modulation kinds, so AM and FM. And if we try to understand our FM signal, you see that we change our carrier frequency with the modulation. So if we talk into our radio with AM set, we change our HF frequency by our audio signal, and that is what we really can see here. If we have here, for instance, in the middle our carrier frequency, and then we modulate it, you see that we are changing our HF frequency. And on AM we just change our amplitude, so we do not change our HF frequency, so that will always stay the same. We change our amplitude, and we do the different thing on FM, so we keep our amplitude, but we change our frequency, and that is the difference between these both modulations. Okay, and back to our spectrum analyzer screen. So we were able to see the audio frequency on our AM signal, because we simply needed to see the difference between the carrier and our first tone, up and down, so upper sideband and lower sideband, and we saw that it is only 1 kilohertz. Now we have to deal with two parameters. One is of course our audio frequency, and secondly it is our deviation. So first of all, we are able to find relatively easily our audio frequency. Okay, and I want to show you that. So if with this signal here, if I put our span again to 10 kilohertz, so that is what I want to do right now. So we put it on 10 kilohertz again. That means from here to here we have now 10 kilohertz in display, and here in the middle, this one here is our center frequency, which is, you can read it down here, 28 megahertz. Okay, now it is relatively easy to see what our audio frequency is, because again we can simply count it here, and you see our tones here are always 1 kilohertz away from each other, and that is the audio frequency information. So that is really very easy to find our audio frequency. But what we do not see here, we can't see our deviation. But as I told you, deviation is very, very important. So let me go back here to a form where we can see the entire signal, and that is here what I have. And I have here a dedicated deviation, and now I increase my deviation to a higher deviation. So let me show you what that means. I put now a higher deviation here to the signal and see what happened. So suddenly our signal is much wider, and let me go here to another resolution, and again I go down to a lower deviation, and you see it right now. You see that our signal is narrowing up, and now again I go up to a higher deviation, and you see now it is wider. So that means you need a wider channel, otherwise you would splatter in the next channel. So as higher we put our deviation, as more bandwidth we need. Okay, but what else is in our deviation? Is it only the channel space you need, or is there another information into that? And that is now the next question we try to answer. Alright, and we have seen this graph or this picture before on the monitor, And again, so if we see what is happening here, we see if this is our frequency, our carrier frequency, we see that we change our carrier frequency with our FM modulation, and we do two things. First of all, our audio, and second, our deviation. And basically what it means, so you see that we are spreading out here our signal. And now the information which is in here is very simple. As wider you go with your deviation, if you have a great deviation, that means your signal is really loud, and a very little deviation means the audio volume is very low. So you always try, of course, to put your deviation to the point where you have the maximum volume on the one hand, and on the other hand you try to keep into your channel width, which is dependent on the radio you are using, okay? And secondly, so this here is, as I said, the deviation, and depending on how wide this deviation is, so that is for volume, and as faster this movement is, so that means you are changing the audio tone, okay? So if it is going very, very fast, then it is a higher tone. If it goes more slowly, it is a lower tone, okay? And of course, a lower tone can have a higher deviation, or it can have a little deviation. And of course, a higher tone, audio tone, can have a low deviation, or it can have really a high deviation. So that is what you have into this information. And of course, you may already understand that we really need to know our deviation because it has to be set to the radio, so we have aligned it that it never will go out of channel, okay? With FM modulation we have one very important parameter, and that is the modulation index M, and that is simply delta HF, which is finally our deviation and our audio frequency. And with this both parameters we get our modulation index, and that is very important because we will now see how we can find with the modulation index, or basically with this formula, our deviation, which is delta HF. But first of all, one example. So delta HF may be, so our deviation may be 5 kilohertz, so that is not unnormal. So that is for FM radio, for VHF, UHF radios. In amateur radio we have 5 kilohertz, so that is very normal. And let's take our audio frequency of 1 kilohertz, okay? So we now see that our modulation index is 5, okay? And this is important because we have simply 3 different kinds of FM modulation, or if you like, angle modulation, because finally it is phase or angle modulation or FM modulation, so that is very similar. And we have to distinguish three different kinds, and that is small or narrow band FM or angle modulation. So that means where our modulation index is smaller than 1, or we have our let me call it a wideband, where it is between 1 and 10 modulation index, or we have our ultra wideband modulation, where it is greater than 10. So let me write it down that you see what I mean. Okay, and here it is. So we have here again our three different conditions, and if we really have a narrow band FM where the modulation index is smaller than 1, then our spectrum analyzer screen looks like AM modulation, and we only can distinguish it if we demodulate the signal. But that is not so interesting to us, as ultra wideband FM. So that is not important to us, because that is more the broadband modulation index. So we working on wideband, so that is quite normal to amateur radio, and that means we have a modulation index between, I don't know, 3 up to 7. So that means for us this here is the most important area where we work into. And the method we are getting our deviation out of our screen signal, our spectrum analyzer signal, how we can get out the deviation is only valid here for our wideband FM. So that means for the modulation we are normally working with in our ham radio or CB radio world. Okay, and now we are using a little trick to get to our needed deviation, and we gonna convert this formula simply to our delta HF. Okay, so because that is finally our deviation, and that means if we convert it here, delta HF is the same like our deviation, okay, is the same like our modulation index times our F audio. Alright, so that is now only this here is converted to this formula, and this here is the formula we can finally use to find our deviation, because this here is what we are looking for, as it is not so simple to see it directly in our spectrum analyzer picture. Okay, and you already may wonder why this converted formula will help to find our deviation, and that is now what I want to show you. So I have connected here my audio generator to our HF generator, and you see we are using here 1 kilohertz. Okay, hopefully you can see it, so let me go a little closer that you can see it. So we are using here our 1 kilohertz, so that is what we have used the whole time. And now what will happening if I change here my audio frequency? Alright, so let me go back here to our signal on the spectrum analyzer, and that is what we have seen all the time up to now. And now let me change simply our audio frequency, and now I start changing the audio frequency and see what's really happening here to all the different tones. And of course, very important to us is here our fundamental tone, which sits here on our carrier, 28.0 megahertz. And when I'm changing here, you can see it hopefully. When I'm changing here my audio frequency, and that is what I'm doing here, you see that the amplitudes of our spectrum, so the single amplitudes, are changing. So from high to low, so see, this is here our center, our carrier, so now it is quite low compared to the other tones. And if I go changing here our audio, you see that really our tones and amplitudes are changing quite a lot, and that is very, very important to us. And again, so for instance, I'm using now for instance 2.1 kilohertz, so that is the audio frequency, and that is definitely an audio frequency we still using within our modulation with or our voice modulation we are using in our band 2.1 kilohertz, because that is in our normal speech. So of course our speech is not only on 1 kilohertz, so that is a permanent changing audio frequency, so that is for sure. And you see on our spectrum analyzer screen that this will obviously have an impact on our amplitude here of the different tones, and that is very interesting and important to us to find finally our deviation. And therefore our Bessel function will help. And don't worry, we do not go into that mass, but the Bessel function finally is what will help us to determine our deviation. So let's see here a graph again from Wikipedia. And finally, Friedrich Bessel, who lived from 1784 to 1846, he found the Bessel, or so-called the Bessel function, which is a differential function, differential formula, and with help of this Bessel function we are really able to find the deviation. But once again, we do not go into this mass, we only are interested in the practical aspects of what he found. Bessel functions are the radial part of the modes of vibrations of a circular drum. So you see, when Bessel found it, it was acoustic, think, but as you can see it here in this graph, so that can easily convert it to our sine wave, and can so simply convert it to electronical aspects, and that is what it is finally. So we convert his findings to our modern electronic, and you already can see here the waves, and this is absolutely the same behavior on our carrier, and yeah, finally on our modulation. And what you have seen in the animation before, you can see here in the graph. So we have the different graphs here, and the J0 is, let me call it the fundamental, and you see here of course we have the peak, and then we have here a 0 point, okay? And if we follow our J0, we see that we have of course more than only one 0 point. Important or very, very interesting for us is the first 0 point, because we really can work with this first 0 point, because you can see it here already, delta phi, the first 0 point is at 2.4, right? And well, it is exactly 2.4048, but we do not need all these digits. If we only know that the first 0 point finally is at 2.4, then we can use the first 0 point when our wave is going through 0, okay? And when we know that is at 2.4, we really can go ahead with this information. Okay, and when we already played around here with our audio frequency, we have seen that our center frequency, so our carrier 28 megahertz, is so the amplitude is going up and down. And that is simply indicating that there is a 0 point of our Bessel function. And what we are really looking for is the 0 point of our fundamental, because that is equal to the Bessel 0, our first Bessel 0 at 2.4048. So that is then the first 0 point. And because it might be confusing, because we have seen we have more 0 points than only one, I would suggest to simply start with a very low audio frequency, and therefore let me simply go here to, so this is now 100 Hertz, right? So our audio frequency is 100 Hertz, and that is the graph for 100 Hertz. And now we know that we have here in the middle our center frequency of 28 megahertz, and now I'm increasing here my amplitude, sorry, not my amplitude, my audio frequency, and you already see that we have here, of course, a changing spectrum, and let me increase it more and more. And again, we are looking here for our center frequency, we need to find our 0 point, our first Bessel zero. And let me increase it more and more. And you see the center frequency is going up and down. And again, it's going up, up. And I'm increasing by 100 Hertz, so that is now 1.7 kilohertz audio, 1.8, 1.9, that is 2. And you see our frequency is going down. So let me carefully increase here or change the resolution, and let's see if I'm able to get here my fundamental or my carrier frequency almost to 0. And what you can see here, more or less. So, and I'm playing here a little bit with the audio frequency. And now, what you can see here, our fundamental or our carrier frequency is completely vanished. So it is gone. And that means this is now our Bessel 0 point, and that is exactly our audio frequency we need to find our deviation. And now let's go over to our audio generator, so I do not make any changes here. And you see the audio frequency where we have our Bessel 0 with the deviation I have set to my HF generator. For this combination, 2.064 kilohertz is Bessel 0 of our center frequency of 28 megahertz. Alright, so let's go down to our formula. And we have used this formula here. So what we said is that our deviation is the modulation index times audio frequency, right? And we have seen that our Bessel 0 is at 2.4, okay? So for our modulation index, we simply set our 2.4. And that means our formula we are using now is deviation is equal to 2.4 for Bessel 0 times our audio frequency we found where the carrier is almost 0. And that was 2.064 kilohertz. And now let's see what that means. So I now type in 2.4 times 2.064 kilohertz. All right, means this is 4.953 kilohertz. So is the deviation what I've set here to my HF generator, is it really 4.953? Okay, so I do not switch off my camera. So I directly go over to our generator. And what can we find here? So you see our FM deviation is 5 kilohertz. Okay? So that means obviously that we were really able to find with our formula and with our Bessel 0, we were able to find finally our deviation, which is 5 kilohertz. And that is awesome, isn't it? Well, but maybe you cannot believe it, so maybe I have done something. But anyway, so we leave now everything alone, so we do not touch any instrument. The only thing we want to do, we want to change with our spectrum analyzer into an analyzer mode, and therefore our analyzer mode is analysis mode is up here, and I change to analog demodulation. And now we get here our entire information about the signal we have here. And I hope you can read the important information. So let me see that we can get here all figures we need. I really hope that you can read it, because we have here the informations, and we have here our FM demodulation, and what we see is that our peak plus and minus, so that is our deviation, is 4.99 whatever, so approximately 5 kilohertz. So plus and minus, because of course we are right and left beneath our carrier, and therefore we are always measuring plus and minus. And you see this here is definitely our deviation, and you see here our audio frequency, and that is exactly what we have on our audio generator, our 2.64 kilohertz. Okay, let me zoom in, maybe then you can see it much better. Once again, here is our deviation, and here is our audio frequency, and again that is what we have here, our 2.64, and you have seen the deviation shown on the HF generator, and that means we are really able to find with our Bessel zero our deviation, and therefore that is the method you are able to determine the informations you need of a FM signal. Well, additional to that, and that is really the beauty here of my signal hound. So my signal hound is really able to give me the deviation, it is able to give me the audio frequency, but additional to that it is able to give me the synod and the THD. So for the signal we are working on, you see our synod is 50.6 dB, and our THD is 0.15%. So you see that are really nice figures, and yeah, so we really have all the analyses we need here with our signal hound. All right, I hope that is what you was looking for when you ask for more information on FM modulation, and to see how FM modulation looks like on the spectrum analyzer, and how you are able to determine finally the deviation, and of course as well the audio frequency, how you can do it on your spectrum analyzer. And with this method you are always able to get all the information you need to adjust your radio in a proper way. Okay, so that's it for today. Hope you enjoyed it, and if you like it, please give me a big thumb up, and catch you next time. Bye!